Let us recollect what we learned so far about the oscilloscopes. There are two types of oscilloscopes. The analog one, we simply call it as cathode ray oscilloscope, which is slowly fading away due to the invasion of digital instruments. The digital storage oscilloscope has three versions. We have a digital storage oscilloscope, is only for analog inputs. Then we have mixed signal oscilloscopes, which will take analog and digital inputs. When I say digital inputs, it is binary 1-0 variation. And we have the logic analyzers, which are also oscilloscopes, which display only digital signals, right. And the logic analyzer, all these oscilloscopes have certain basic characteristics. We have the sensitivity on the y axis, the number of channels on the y axis, the sensitivity on the x axis in terms of milliseconds per centimeter or microseconds per centimeter, and we can also have two time bases instead of one time base. So, we have dual time base. So, it is immaterial whether I have CRO or DSO or MSO. You can have varieties of oscilloscope. You have single channel DSO, you have single channel CRO, you have dual trace CRO, similarly you have dual trace DSO or MSO. You also have dual time base CRO. Similarly, on the digital side you have dual time base digital storage oscilloscope or mixed signal oscilloscope, right. In this we looked at the inputs. The inputs, especially the analog inputs, have been standardized for the oscilloscope. The input connector itself is what we call the bionet connector or BNC. The input impedance is also kind of standardized. It is 1 mega ohm, approximately 47 picofarad. This can change depending upon the oscilloscope and things that you connect, right. And so that would be your Y1 or Y2 input, and most of the oscilloscopes will give you only 5 volts per division at the maximum or minimum sensitivity, maximum voltage. And we already know on the y axis there would be 8 divisions. So, if it is 5 volts per division, the peak to peak of any signal can only be 40 volts, right, 8 into 5 40 volts, right. So, because 5 volts per division or 5 volts per division centimeter would give me 80 volts peak to peak, right. And if you want to see higher voltages, for example, we want to look at the supply waveform, the 50 hertz power supply waveform. We know the peak will be 230 into root 2. So, I will have the peak to peak 230 into 2 root 2, 460 into 1.414, right. So, which means if I need larger attenuation, not amplification, I need to bring 230 into 2 root 2 to plus or minus 40 volts, so that I can see it on the oscilloscope, right. So, we use what is known as divide by 10 probe. If this is 1 mega ohm, we keep 9 mega ohm, right. And so, for DC, if I look at it, 1 divided by 9 plus 1, right. So, if I say this is V oscilloscope and this is my V input, V oscilloscope by V input would be 1 mega ohm divided by 1 plus 9 mega ohm is equal to 1 by 10. So, my oscilloscope input becomes 1/10 of the input I am checking with the probe, the tip of the probe, right. So, we call this as a divide by 10 probe. Similarly, if I keep it as 99 mega ohm, I will get a division of 1 by 100, right, 1 by 100 probe. 1 by 10 probe is quite popular, 1 by 100 probe is not very popular. Most of the oscilloscope manufacturers, when you buy your oscilloscope, they will automatically give you 1 by 10 probe along with the oscilloscope, right. But if you want 1 by 100 probe, you need to specifically order, right. Now, if I look at this way, I will not get all at all frequencies 1 by 10. For DC, the capacitance is open circuit, so I get 1 mega ohm by 10 mega ohm, 1/10. So, if I look at for AC, the impedance, I call this as R oscilloscope, C oscilloscope, then I call this as R probe, right. The division, right, V naught as a phasor of function of a frequency would be R1 R naught into 1 by j omega C naught divided by R1 Rp plus R naught plus j omega C naught, right. Oh no, let me write it clearly, one more step. So, I have this impedance which is R naught by into 1 by j omega C naught divided by R naught plus 1 by j omega C naught divided by the total impedance is R1 Rp plus R naught into 1 by j omega C naught divided by R naught plus 1 by j omega C naught, right. So, this if I look at it, if I bring this here, so this would be R naught R oscilloscope divided by 1 plus j omega C 0 R 0, right, divided by R p plus R naught divided by 1 plus j omega C 0 R 0. So, this works out to, if I bring this here, R naught divided by R p into 1 plus j omega C naught R naught plus R naught, right. So, the as omega increases, this quantity will increase and I will not get R naught by R naught plus R p, right. I will get something completely smaller, different, smaller. So, if we the moment we look at this network, we know from the equation as well as from the look of the network, right, we know that is a low pass function, right, because at higher and higher frequencies the impedance of the capacitor will be lower because it is 1 by j omega c, right, and hence I will get the ratio smaller and smaller. So, if I look at frequency versus V naught by V I, it will start at 10, but it will slowly start reducing, right. This is not good because we are going to use an oscilloscope for measurement, and if I am going to get a division by 10 at DC and division by 7 at some other frequency, right, it is not a good one, right. Even if I know the division, it is not a good characteristics. So, I would require, or anyone would require something like this. It is 10 independent of frequency, right. So, now what we do is this, we put another capacitor, we also add another capacitor, I call this a C variable, right. So, if I look at the division now, this impedance by this impedance will be the division. So, I have V naught is equal to, this impedance is, here we have R naught by 1 plus j omega C naught plus C variable into R naught, right, divided by the total impedance. So, I have Rp Cp Rp divided by 1 plus j omega Cp Rp, right. This impedance Z1 Z2 by Z1 plus Z2 will work out like that, plus of course, I have the same R naught by 1 plus j omega into C naught plus Cv into R naught into Vi, right, at any given frequency. So, this would work out R naught divided by, if I bring this here and multiply with this, I will get R naught plus Rp into 1 plus j omega C naught plus Cv into R naught divided by 1 plus j omega Cp Rp, right. Now, when I put omega equal to 0, which means DC, this term vanishes, I get R naught by R naught plus Rp, that must be 1/10, right. So, for DC, right, R naught by R naught plus Rp must be equal to 1 by 10. So, this leads to R naught is equal to Rp, or let me put it this way, because we are going to put the probe resistance, R naught is constant 1 mega ohm into 9, right, 9 times R naught. Okay. So, if I put Rp as 9 times R naught at DC, this omega will be 0, this omega will be 0. So, I will get 1 by 1. So, I will get R naught by R naught plus Rp, and I will get 1/10. Now, for any frequency, if I want the same 1/10 to be there, right, at any frequency also I should get R naught by R naught plus Rp, which can happen only if this quantity within the bracket is 1, right, it must be 1. So, that leads to, for AC, if I want to get V naught by Vi, V naught by Vi at any frequency to be 1/10, right, that leads to 1 plus j omega C naught plus Cv into R naught must be equal to 1 plus j omega Cp Rp, right. So, now I can cancel 1 1 on both sides, j omega I can cancel. So, I have C naught plus Cv into R naught is equal to Cp Rp, right, or C naught plus Cv is equal to Cp into Rp by R naught, right. We already know what is Rp by R naught, 9, right. We have just now derived Rp by R naught must be 9 for the probe to have 1/10 division at DC, right. So, this must be 9 times Cp, right. So, we vary this capacitance Cv, the variable capacitance, so that we have this condition Cp 9 times Cp is equal to C naught plus Cv. C naught is already inside the oscilloscope, right. So, this is already inside the oscilloscope, right, and this one is the probe that comes on the probe. So, the variable capacitor will be on the probe, right. You will have a small screwdriver with which you can adjust, which means after I connect I need to check whether this condition is satisfied, which is very difficult, right. Measuring of capacitance, 2 capacitances, and finding that the ratio has to be 1/9 or 9 times, right, is very, although these are small capacitance, picofarads, right. So, people realize there must be an indirect way of achieving the same condition, right, without actually measuring the capacitances, right. That is where the square wave comes into picture. If I have a square wave, I am putting a symmetrical square wave. So, it is easy for us to understand, it need not be symmetrical, I can even put unipolar square wave, right. If I look at the square wave, I have T by 2 T and I have plus V here minus V here, right. The square wave can be thought of as sum of series of sinusoids, right. So, this would be equal to I have the fundamental plus third harmonics. I said third harmonic, second harmonic will be absent, because Fourier series tells us that if the waveform is symmetrical about the x axis, even harmonics would be absent. So, I will have fundamental frequency, third harmonic, fifth harmonic, all harmonics, right. If it is a perfect square wave, all harmonics will be there. Now, if I connect this to the probe, if all harmonics are faithfully reproduced on the oscilloscope, I will get a square wave, right. If I look at it, I will get the same square wave if the condition V naught phasor by V I phasor irrespective of omega is equal to 1/10, right. Now, assume that the high frequencies are attenuated. I have not matched this, C naught plus C V is more than 9 times C P, right. Then what will happen? My probe would start behaving like a low pass filter, right. The probe will start behaving like a low pass filter, my high frequencies are attenuated. So, if I look at the square waveform when high frequencies are attenuated, I will get a waveform like this. This is, I am really exaggerating, but the corners will not be corners, right, they will be slightly sloped at the corners. This is a worst case attenuation, right. Deviation from the expected C naught plus C V is equal to 9 times C P is very large, right, the deviation is very large. Now, if I have the condition that C naught plus C V is less than 9 times C P, right, this network will become a high pass filter, right, which means higher frequencies would be amplified, right. So, I would get a waveform right, something like this. So, every time there is a 1 to 0 transition plus V to minus V transition, there would be a small ringing, right. So, in this case I know I have to increase CV, in this case I know I have to decrease CV, and if I get a perfect square wave on the oscilloscope, I know that the condition C naught plus CV is equal to 9 times Cp has been met, right. So, all oscilloscope will provide an output of 1 kilohertz, and because they anyway provide an output of 1 kilohertz, they also make this as 1 volt instead of any arbitrary value, right. It could be 0 and 1 volts, or it could be plus 1 volts and minus 1 volts, depends upon the manufacturer, right, but it will always be 1 volt, right. So that you can also check the Y calibration, right. You know it has to be 1 volt, and if you put 1 volts per division, I must get 1 division. If I put 500 millivolts per division, I should get 2 divisions, right. So that also can be checked on the oscilloscope. Some oscilloscope manufacturers also give you 100 millivolts apart from 1 millivolt. So when you are going to use a divide by 10 probe, the first thing that you have to do is put the probe on the output available in the oscilloscope, right, the square wave output, trim the capacitance on the probe, the variable capacitance on the probe, such that the square wave appears as a square wave, not as a corner rounded off or with ringing, right. You should move the capacitor adjusting screw, and so that you get the perfect square wave. So this is known as the tuning of the probe, and you must do it before you use a probe. It is the same whether it is 1 by 10 probe or 1 by 100 probe. Only thing is, in the 1 by 100 probe, C naught plus CV must be 99 times Cp. That is the only difference. Now, so far we have learnt about the oscilloscope, which is an instrument that enables us to view the actual time varying quantities, right. And though the oscilloscope was originally invented along with the analog indicating instruments, today most of the oscilloscopes have gone into the digital side, right. So we now start learning about digital instruments. We specifically put digital indicating instruments. Because there are digital instruments which do not have an indication to be read by a human being, right. These are normally connected to machines, and those type of instruments we will not see now, right. So when I say indicating instrument, in the analog indicating instrument, we saw in most cases a pointer was continuously moving on a scale, right, and the scale itself is marked in certain divisions, right. It could be 100 divisions or 150 divisions, and the from the marked values and the position of the pointer, we can make a reading, right. We do make a reading, right. And in that, if I look at the position of the pointer, the pointer can be anywhere on the scale, right. It is continuous movement. On the other hand, when I say digital, which means I am going to look at only the number, right, the digit. So these instruments can display actual value in numbers that we understand, right. So it could be, let us say 1.234 volts or 1.234 millivolts, right. So, on the instrument we will have this value displayed, right. So, these kind of instruments we call digital indicating instruments, right. The very first digital indicating instrument that was developed, that was invented, is the digital timer counter. There is also a reason for this. If you want to measure the time period, you can, or the frequency of a waveform, right. The only option open to you is display it on an oscilloscope, measure the time period, then find frequency as 1 by t, right. So, instead people were looking for an instrument which will straight away tell the frequency is 7.375 kilohertz, right. That is the instrument that came first, right. And this was really impossible in the analog domain using analog indicating instruments. People did try vibrating reed frequency indicator, tuned frequency indicator and so on, but they really did not provide a nice reading on the frequency. The digital timer counter, as the name indicate, is a digital indicating instrument, and all digital indicating instruments, even though the final value is the decimal number that we understand, right. If you want to design a machine to operate on the decimal system, it is really impossible, right. And so, when people are trying to make machines to work with numbers, they found out that though the machines are nearly incapable of understanding operating decimal numbers, they do work fine with the binary system, right, where I have only two levels, 0 and 1, and because there are only two levels, we can distinguish them very easily using any circuit. I can say, in we all know in the transistor logic, 0 is any voltage between 0 volts and 0.8 volts, and the 1 is any voltage above 2.4 volts, but below 5 volts, right. So, that kind of a tolerance possible to make the zeros and ones made the binary system the system for machine operation, machine computing, right. The problem is binary system is nice for instruments, but it is not very nice for us, right. In the binary system we start with, for 0 of course we have 0, so this is decimal, this is binary, and I have 1, I also have 1, nice. Now I have 2, because I have lost all the available symbols in binary system, I will have to add one more place, so I have 1 0. If I have 3, I have 1 0 0. If I want 4, I need 1 1 1, right. 4 I need 1 0 0, 5 I need 1 0 1, and so on, right. Now, if I really look at a number which says 1 0 1 1 0 1 1 1 1 0, I can't understand what it is, right. On the other hand, if somebody tells me that is 1.234, I do understand what it means, right. So, which means you must be able to operate on both sides. You operate at the machine level with binary, you operate on the human interface with the decimal, right. This resulted in a system called binary coded decimal system or BCD system, right. In the BCD system we use the binary at the machine level, but we use the decimal system at the interface or human interface level, right. The human interface is normally the display that comes at the end, right. In the binary coded decimal system we have 3 bits, so I call this as bit A, bit B, bit C, and bit D. So, we have 0 0 0 0, that is 0 right, and 0 0 0 1, that is 1, 0 0 1 0 2, 0 0 1 1 3, 0 1 0 0 4, 0 1 0 1 5, 0 1 1 0 6, 0 1 1 1 7, 1 0 0 0 8, 1 0 0 1 9. So, we have this is decimal, this is the binary. So, with 4 bits I can represent all the 10 binary symbols 0 to 9, right, and any digital system that operates on this principle. Of course, if it is final binary, I can go to 1010, which will be 10 in decimal, 1011 would be 11 in decimal, or we can go to hexadecimal and start saying 9 A B C D E F, right. But because these instruments, indicating instruments for human consumption, we always operate on the BCD, right. So, if we have a BCD so now I have each bit right. So, this is B A, B B, B C, bit D, right, and each one on the binary system I need a flip flop to take care of each bit, right. Now, if I connect these flip flops in a daisy chain, I take the Q output of the flip flop, right. Oh, I think I made a mistake. B A, B B, B C, and this is B D. This is my input. So, this is my input, input, input. Flip flop can be a toggle flip flop, JK flip flop, right, any type of flip flop. And I start giving my binary input here 10 10 10. Right. Assume that this is a toggle flip flop, T flip flop. I will get, this is my input, right. At this point B A would toggle for every period of the input, right, assuming that my toggle T flip flop is rising edge sensitivity, right. I can derive that B A would be divided by 2, right, and B B would be B A divided by 2, and B C would be B B divided by 2, and B D would be B C divided by 2. So, I get successive division by 2, and if I start looking at the waveforms, I will see that the first clock here, right. Now, I have put a term, I call this as a clock, right, will make this 0 0 0 1, right. Assume that all are 0 in the initial stages, B A is 0, B B is also 0, B B will be something like this, right, divided by 2, this is B B. So, at the start, before I apply the clock, everything is 0, B A, B B, B 0, right. So, the first class will make me B A to be 1 and B C D would be 0. So, I will get the first clock 0 0 0 1, right. When the second clock comes, B A would go to 0 right, but BB would become 1. Oh, okay. What this is? I have rising edge sensitive. So, I will have 0 1 1 1, right. The next clock will give me 1. So, if we do go through clock by clock, I will see that this flip flop system will go through 0 to 9, and of course, beyond 9 A, B, C, D, E, F, right. So, if I take the reset pen of all the, right, RST, 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 and then connect my B3 and BD to an AND gate and connect it to reset, right. So, when I go from 1001 to 1010, this is BD and BB. So, these two will become 1, the AND gate will become, output will become 1, and it will reset all the flip flops. So, after 1001, when 1010 comes, it will go back to 0, right, the flip flops will be reset to 0. We call this as ripple counter, because the ones and zeros are rippling through from right to left, right, and this is not a very good design, okay, because there will be a small glitch when I go from 9 to 0. There are different forms of counters, right. They really count the number of clock cycles given to them, right. So, if I look at the output BA, BB, BC, BD, they count the number of clocks that is given, right. You have synchronous counters, right. There are several types of counters possible. So, the basic building block of the timer counter is this BCD counter, right. So, we can say I have one BCD counter, I will have, I call this as A1, B1, C1, D1, there are 4 outputs, and I have a clock input and I have a carry output. The carry output is the AND gate output that tells me that there is a rollover from 1001 to 1010, because a binary coded decimal, the 9 must be sensed, and when you go to 10 you should reset it to 0000. So, that signal which converts the output, or which forces the output to go to 0 at the transition from 9 to 10 is called the carry, right. So, we can again make another BCD A1, A2, B2, C2, D2, right, and the clock of that I can connect from the first BCD counter, right. So, now if I look at it, every time this goes through 0 to 9, I will get a carry, and that carry becomes a clock, and the A2, B2, C2 will now count the number of times that I have got carry, right. If the first counter has gone through 0 to 9, it has counted up to 10, right, and goes from 9 to 0, one clock will be generated in the carry and A2 will become 1, right. So, this will go to 0 to 9, and the next one, this will become 1 and this will become 0, right. Once again this will go to 0 to 9, let me put it as 0 to 9, and this will become, carry will become 1 and this will become 0 to 9. Again when it rolls over, right, I will have 1 0 which means 2 and I will get 0 to 9. So, if I now look at the cascaded BCD counters, 2 counters, I can now represent in binary the BCD numbers 0 0 to 9 9, right. Of course, after 99 the carry will be set and it will go to 0 0 to 9 9, right. So, that will keep on repeating if I keep increasing, keep on feeding the clock, right. So, now I can put this carry into another BCD counter. I call this as A3, B3, C3, D3, the 3 ABCD bits. Then I can now count from 0 0 to 999, right. So, I have what is known as a 3-digit BCD counter, right, 3-digit BCD counter. This will simply count the number of ones and zeros, right, the 1 0 transition or 0 1 transition depending upon the type of logic we use, right. If you use leading edge sensitive or rising edge sensitive, it will change, all things will change when a 0 to 1 transition occurs. If I put a trailing edge or sensitive binary circuit, then the changes will occur from 1 to 0 whenever 1 to 0 goes through. It does not matter as far as we are concerned, the outputs, the BCD numbers of these counters will now count the number of clock that is fed to the counter from 0 0 to 999, right. So, if I look at it, there are 999 levels, right, and if I include 0 level, I call this as a 1000 level counter, right, or simply 3-digit counter. Okay. Now, if I want to look at this output, one way is look at this output 1001. So, this is 9, this is 0001. So, this is 1 and this is 0011. So, 319, right. That would be difficult, right, that would be difficult for a human being to decipher the binary into the BCD binary coded decimal into decimal, right. So, instead it would be nice if I can straight away display it as decimal numbers, right. So, initially people had lot of difficulty with displays, right. The very first display that was made was they had another binary, right, circuit which took A, B, C, D, right, and then provided 10 outputs 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, if A, B, C, D is 0, 0, 0, 0 output will be active. If A, B, C, D is 0, 0, 1, the 1 output will be active, right. So, we call this as BCD to decimal decoder, right. We still have an IC in the CMOS logic family CD4017 which will do this job, right. And then you have a system 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then if this 0 is enabled, you make that display glow, right. Just put a bulb at the back and then the 0 glows. If my 1 output is there, 1 glows, right. So, this way we can display 0 to 9. This was the first digital display that was made, okay, long back. Then people decided when it looks awkward, right, one has to really look at where the display is glowing, right. It would be nice if the same portion, right, instead of having different portions for different right. The same portion displays 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that would be really nice, right. So what they did was they used the depth, right. So 0 was at the first, right. So this is 2, this is 3, right. I mean you put a 0 in the front, 1 at the back, 2 further backwards, 3, 4, 5, 6, 7, 8, 9. It is the same position, but the display will be one behind the other. If you want to do that, then you cannot put a conventional bulbs, right, because one bulb will obstruct the other bulb, right. They came up with a nice display system called NIXI or neon display system, right. So these are just anodes which when energized will glow, right. So the first anode will be shaped in 0, the second anode would be shaped in 1, 2 and so on. So if you look at it, the displays will go in and out, right. If 9 is displayed, that will be some maybe 4 or 5 millimeter inside, and 0 would be at the first. People also optimized, right, which one should come first, which one should go second and so on. So this kind of displays were there for quite some time, right, till the late 60s, 1960s, and then people devised a very ingenious method of displaying numbers called the 7 segment display. Which we are all very familiar with, but it took a long time for people to invent the 7 segment display. In the 7 segment display, there are 7 segments as the name indicates. We call this A, B, C, D, E, F and G, right. And sometimes we also have a small point here called decimal point, dp, right. Most of the 7 segment display are actually 8 segments, there will be a decimal point, right. Now if I want to display 1, all I have to do is, right, let me put it here, I put A and B, right, I glow A and B, I will display 1, right. If I want to B and C, sorry, B and C, if I want to display 2, I enable A, B, G, E and D, right, that would be 3, right. And if I want to display a 0, I will have to put A, B, C, D, E, F, right, A, B. So it is possible to display numbers 0 to 9 using only 7 segments. So if that is a display, then we do not use this circuit, we use what is known as the BCD to 7 segment display driver, and there will be 1, 2, 3, 4, 5, 6 and 7. So A to G, and we have the 7 segment display, right. Okay. So initially the 7 segment display, the segments were bulbs, right, literally incandescent lamps. Then when LEDs were invented, it became LEDs, and most of the 7 segment display today we use are the liquid crystal displays, right. That is because the liquid crystal display consumes the least amount of power, right. So we will stop here, we will continue in the next class.